Alright, today we got multiplying and dividing radical expressions. When multiplying two radical expressions, use multiplication property of radicals right here. And this is just saying you take the two things that are inside the radical, as long as they have the same index right here, and you multiply them together inside the radical. Okay, so yeah, big thing is make sure they have the same index, and then multiply the outsides with the other outsides and the insides with the other insides separately. And then simplify if possible. So we're going to take all these here and simplify them down here. So the first thing you're going to do here is look at the 4 and the 2, multiply those together. That's going to be 8. And then you're going to do the cube root, and then 3 times 7 right there is going to be 21. All right, and then from yesterday's lesson, we talked about simplifying and making sure you don't have any pairs, or in this case, groups of 3 items right here, and this only has 2 things right there, so this is actually fully simplified as much as we can do. That will be it there on that one. Okay, now sometimes you'll have examples where you don't have a number out in front, so I guess you could say that the implied number is 1 out in front. 2 times 1 will be 2. And then you have 30 times 12 right there, which is going to be, I guess, what is it going to be, 360, kind of like 3 times 12 right there. And then 360, we can actually break that down. All right, and if you're not sure what multiplies to 360, you could probably go actually with 30 and 12, actually. And then we can break down 30. I guess you have 5 and 6. And then 6, you got 3 and 2. 12, you got 3 and 4. And then 4, you got 2 and 2. And since this is a square root, I see that I got a pair of 2's right here. I got a pair of 3's right there, and that's the only pairs that we have. Okay, so we'll put 3 times 2 outside of our radical. And I guess we have this 1, 2, and then that 5 left over inside the radical. And then we have the 2 that we started with right here outside of the radical as well. So you got a bunch of things that you're gonna have to multiply all back together. 4 times 3 times 2, that's gonna be 12, I believe, and then 2 times 5, that'll be 10. So that'll be 12 square root of 10 right there for that example there. So multiply the insides, multiply the outsides, and then simplify if possible. Okay, next one here. Looks like you got 8 times 3 right there. I guess we'll go to that as 24. And then you have some variables going on. You have x to the 5th times x to the 1st power. And our power properties here say that we need to do that as, we need to go and add the powers. That'll be x to the 6th right there. And then square root of all that stuff. All right, and then the rest of this is from yesterday, just simplified radical. I guess we can go 6, 4, go 2, 2 for the 4, and then 2, 3 for the 6. Got a pair of 2's right there, so we'll pull a 2 out. And then the 2 and the 3 don't have pairs, so multiply those back together. That'll be 6 inside the radical. And then actually, x to the 6. From yesterday, we talked about taking that, and if it's a square root, divide that by 2. That'd give you 3 full groups. And then we'll go ahead and say that the final answer here is x cubed right there. So the square root of x to the 6 is x cubed right there. So just divide by 2, and then you get your groups. And if you need a recap on that, go watch the 9.1 lesson. Okay, next one here. Check if the index is the same. They are to the 4th power here. And I guess we're going to do 20 times 20. So that'll be 400. And then we got the 4th root of 400. We'll take care of that here in a second. Your powers of x, you'll have x to the 6th, and then y to the 7th. And then it's now just like a problem from yesterday. So 400, we're looking for groups of 4 things here. So I would probably go 4 and 100. 100, you could go, I guess, 10 and 10. You can go 2, 5, 2, 5, and then the 4, you got 2 and 2. So you actually have a group of 2's right there. You're looking for groups of 4 items right there. So you have 4 2's right there. So you're going to write the 2 once outside to represent the group. And then I guess you're going to have the two 5s left over inside. So we'll put the 5 times 5 on the inside right there. That'll be 25. Okay, x to the 6. How many sets of 4 do you have there? If you do 6 divided by 4, you'll have one full group, or you could say, how many times does 4 right here go into 6? It goes in one full time. So you'll have one full group right there, x to the first. You don't need to write to the first if you don't want to. And then, you'd have 2 left over after that right there. So yeah, that would be 6 divided by 4. How many times does 4 go into 6? It's one full time, and then with a remainder of 2. So those last 2 x's stay inside the radical. Now you do the same thing with y to the 7th. How many times does 4 go into 7? Once again, it'll be one full time, but then this time there will be 3 left over. And this would be this full thing here simplified. One thing I just noticed here, I almost forgot to write my index right up there, so make sure you write your index on that. And I need to make sure I did my other ones like that, which I did. So yeah, don't forget your index. So that is it there on that one. Okay, next we're going to talk about dividing radicals. When dividing two radical expressions, you can use the division property of radicals right here. So if you have division happening here, you can actually go and divide the numbers first. That's basically what the property. Or you can do the total opposite of that. You can take this and then divide them individually, or root them, I guess, individually. I'm not sure why this is formatted weird here across the page, but when dividing radicals, combine under one radical and then reduce before evaluating. And then remember to rationalize if needed, and then watch the sign changes. I can't remember if we talked about rationalizing yet in Algebra 2, but you probably did it a lot in Algebra 1. So like if you had like the square root of 5 over the square root of 2, you can't reduce it. To make it to where it's only one radical, we multiply the top and bottom by whatever the bottom radical is. So whatever this is down here in the bottom, we multiply the top and bottom by that. The reason we're going to do that here is because that becomes square root of 10 up there in the numerator, but then this becomes square root of 4 in the denominator. And we actually know the square root of 4. The square root of 4 is just regular 2. And then you just leave it as square root of 10 in the numerator. So the whole idea of rationalizing is you're trying to get to one single radical. And then if you need extra help on that, you can probably find some videos online for that, or search anything for geometry or try to refer back to geometry. But we're going to use that whole idea. You're going to multiply the top and bottom by whatever the radical is in the bottom. That essentially makes this thing a perfect square or a perfect cube or whatever the type of radical that you have. So let's try it out here with this one. Now, most of the times you want to check and see if it reduces first, because sometimes these problems are going to reduce right from the get-go. So before we do anything with the radical here, we're just going to reduce 18x to the 5th over 2x cubed. Right? And what you do for that is really just divide the front two numbers. 18 over 2 is 9 over 1, or we're just going to say 9. And then x to the 5th over x cubed, that's one of our power rules. We subtract the powers. So then subtract the powers, that's going to be x squared, 9x squared right there. And that's all inside of the radical. Here's the nice thing about that. 9 is a perfect square. Square root of 9 is 3. And then x squared is a perfect square, and square root of x squared is just x. And then that is how you leave it. Okay, so let's see what's going on here with this next one here. Yeah, pretty much the same idea here. Reduce them first. 50 over 2, that's going to be 25. X to the 6 over x to the 4th. When you subtract your powers, that's going to be x squared up there in the top. And then we're going to do the square root of all that. Square root of 25, that's going to be just regular 5. Square root of x squared, that's just going to be x. There you go. Nice and easy there. All right, I guess we have a student here. Maybe they made a common mistake here. Explain the error in this simplification right here. So it looks like you have the 7th root of x to the 5th over the 4th root of x squared right there. So I guess they're trying to do something here with the indexes, and you can't really do anything with the indexes here. You can't even really simplify them here because they have different indexes right there. So you actually can't even use that property that you were using right there. Now there's a couple of things I guess you could do um, to yeah, you could do something here with the powers. I don't think they want us to get into this here, but we do have something. There is a rule here rewriting these as fractions right here. These certain radicals with fractions, but I don't think they were wanting us to go there. So I wouldn't worry too much about that. I would just say you can't simplify this right now. You just leave it like that. Let's see here. Rationalizing. Sometimes reducing will not eliminate the radical on the bottom of a fraction. So this is kind of like the example I showed you up here at the top here when I was talking about rationalization. So like this example right here, you can't divide 16 and 7. So we would have to actually rationalize this here. So we'd multiply the top and the bottom by whatever the square root of the bottom number is. And the whole idea is we're trying to make this denominator a perfect square. So if we can do that, we're going to be in good shape. So the square root of 7 times the square root of 7 is the square root of 49, which some of y'all will eventually say that's 7. Okay, and then we have 16 times 7. Let me go ahead and pull that up here on my calculator. I don't want to think too hard on this. That's going to come out to the square root of 112 right there. And then that is rationalized. Now sometimes after you rationalize, sometimes you can actually simplify your radical down depending on the numbers. So we'll actually simplify this down just a hair. I think as far as what multiplies to 112, well, we know 16 and 7 do. And then 16, you could say that's 4 and 4. And I actually got a pair right there right away. If you got a pair of 4s, you can just write that as 4, square root of 7, and then over 7. And then that is fully simplified, believe it or not. Now, a common question I'll get students that ask is, hey, can we cancel these 7s out right here? And since one's inside the radical, and then the other one's outside the radical, you cannot. So they kind of have different rules going on here. The only numbers that you can reduce are numbers that are outside of the radical together, which in this case, 4 and 7 don't reduce, so you leave it like that right there. So that is going to be it there on that one. Okay. When simplifying, there should not be any radicals left in the denominator, so we will never leave any radicals in the denominator, period. To eliminate the radical in the denominator, we use a method called rationalizing. We kind of already did that. To use this method, multiply the numerator and the denominator by the radical in the denominator. And that will usually take care of things. So I think this one right here is pretty much, it's the same numbers there, so I'm not going to redo that same one there. So we'll jump, I guess, to this next one here. So with this one here, let's multiply the top and bottom by the radical in the bottom. That makes it a perfect square. So we're going to multiply the top and bottom by 5. Or actually square root of 5, I guess I should say. Okay, and then when we do that, that's going to get us the square root of 45. And I guess we still have y squared. And then that's all over the square root of 5 times the square root of 5 is the square root of 25, which simplifies to a regular 5 right there. Okay, and then from there, I think we can actually do the square root of all this stuff here. We can at least do the square root of y squared, that'll be y. And then 45, I guess we'll need to simplify 45 down. It'll be 9 and 5. 9 will be 3 and 3 right there. So this will become 3 outside of the radical, and then 5 inside the radical. So it's going to be 3y, radical 5, over 5, and then that is simplified right there. And I guess, one thing some students might ask here is, can we do something with the square root of 9 from the beginning? You can. You can actually simplify that if you want. At the very beginning, you should still get 3 right there. Kind of a different approach there. Now, here's where it gets a little bit tricky. Whenever you have a cube root, you want to think about what do you need to multiply that makes the denominator a perfect cube. So if you go and do this one here, you need to think about, all right, if I do times 5 right here, 5 times 5 is going to be 25. That's not a perfect cube. So I want to multiply by 5 a few times here, maybe to different powers. That's going to do that there. So if I multiply by 5 squared, or 25 right here, 25 times 5 is actually going to give me the cube root of 125. And that's actually a perfect cube that we can use. So with these specifically here, you want to make a perfect cube. And I would even write that for your notes here, because this might help you out here. Make a perfect cube in the denominator. And if you need to look at like I guess your different perfect cubes, perfect powers of 4, stuff like that, I had that at the end of the video the last video for 9.1. So if you need to refer back to that list, you can. So if I can make this eventually look like a 125, a cube root of 125, we're going to be in good shape. Now, same idea here with variables. The variables are a little tricky here, so I want that eventually to be something that I can divide by 3, some type of power. So if I multiply by the power of y to the first right here, this is going to make y cubed here in the denominator. And that right there in the denominator of this fraction would be a perfect cube. We could do this whole entire cube root right here. Now, whatever you do to the top of or the bottom of a fraction, you got to do to the top of the fraction. We're going to multiply the top by 25 y to the first, right there. Okay, and then cube root right there. So that's going to get us cube root 7 times 25. I believe that is 175, I believe. And then I guess you still have x, and then you got y, or y to the first, whatever you want to write for that. Okay. Now, this entire denominator, if I can talk here, you can actually simplify here. 125 is, the cube root of that is going to be 5. And the cube root of y cubed is going to be y. That's why we chose those numbers, to make it to where it's a perfect cube. All right, now the rest of the stuff here, I don't actually think you can simplify it here. So this is just going to be 175 xy. If you go and try to simplify 175, we already know, okay, it's 25 and 7, and 25 is 5 and 5, but there would be no group of 3 things, or there would be no trio right there, so we can't really simplify this. This is going to be how your final answer is. So those are kind of the newest and the hardest type of questions here. You got to figure out, once again, what do you need to multiply by to make a perfect cube in the denominator with this specific example. So I think we got another example kind of like that right there. This one right here, you got the fourth roots here. So instead of making a perfect cube, you got to make a perfect, I guess, quartic item. So something that has groups of 4 things here. So think of what can we do the perfect fourth roots of here. You can't do the fourth root of 8, but if I multiply that by another 2, you would actually have 16 right there. 16 is going to be a perfect power of 4 right there. We can do the fourth root of 16. Okay, so eventually, we've got to multiply the fourth root of 2. Now we need to handle our variables. We have x squared. If I multiply by another x squared, I would get x to the fourth. We can do the fourth root of that. If you have z cubed right here, if I multiply just by one more z right here, z to the first, it's going to get you z to the fourth. And you can do the fourth root of that. All right, and then whatever you multiply the bottom by, you got to do the same thing in the top here. You got to multiply the top by the fourth root of 2, x squared, and then z to the first. Okay, and then when we multiply that, you're multiplying these two here together. It's going to be the fourth root. You don't have any other coefficients, so that's 2. And then I guess we'll go x squared. If you want to go in alphabetical order, then I guess we'll go y to the 5th, and then z to the first. All right. The entire denominator, the fourth root of 16, you need to know that to be 2. The fourth root of x to the fourth, you have 4 x's there. That's one group of x. And then you got one group of z's right there. Okay. Up in the numerator, what do we have here? Actually, so the numerator, you really can't. Well, actually, there's one thing you can do here. You have all of this here, and you're looking for groups of 4 things right here. Oh, whoops. And it looks like the only thing you could do, the fourth root of right here, you could actually simplify that y to the fifth. You actually have 4 or more than 4 y's right there. So we can go put a 1y out in front, fourth root, 2x squared. If you did y right here, and be careful, this kind of looks like I have, y to the fourth right here. It's really y and then times the fourth root. So it's y to the first right there. So if you see how many times how many times 4 goes into 5 right there, you would have 1 left over. So you'd have y to the first left over, z to the first left over, and then 2xz in the denominator. And then that right there, believe it or not, fully simplified. And that is it there on those. So those will take practice. Those don't come very easy and naturally to people. So just practice them and you will get them down. All right. Then I think they give us 2 problems here where they give us formulas here, and then we just need to apply the formulas and simplify if possible. So I guess you got the formula for this right here. This formula relates the side length of S of the cube in centimeters to its mass in grams for the metal palladium. And then what is the simplest form of the right-hand side of the formula? Use the simplest form, the side length of the cube of palladium with a mass of this many grams right here. So I guess they're basically asking us to simplify it, and then once we simplify it, plug in 324 grams. Honestly, if they're asking us to solve it, I would just plug in 324 right away. But if you want to rationalize, you can also do that as well. You can rationalize ahead of time, and that might make the problem easier. Honestly, I would probably, I would just go ahead and just plug in right away on something like this here. So I'm going to just literally plug in 324 up there in the numerator, and then you got the cube root of 12 right there in the denominator. The reason I want to do that first there is maybe I can actually divide 324 and 12. So I'm going to use my calculator here real quick on that. 324 by 12. Apparently that gives me 27. And that actually makes a perfect cube right there. We can say, oh, okay, this cube has a side length of 3 right there. And units, I guess they said this was going to be in centimeters right here. So 3 centimeters. So usually with these, it's much more efficient to plug in first and then simplify. So, all right, I believe this is the last one. Yep. All right, so you got the volume V of a wooden beam is this formula right here, where L is the length of the beam, and then S is the length of one side of its square cross section right there. If the volume of the beam is 1,200 cubic inches and the length is 96, what is the side length should work? So you're basically plugging in everything you know into your formula that you have. We got the 1,200 cubic inches, the length is 96. So we got 96 and then S squared. I guess we're essentially solving for S right there. So we're going to do this by dividing by 96 first. I wouldn't do anything. I would do the square root as your last step. So 1,200 divided by 96 comes out to 12.5. And then I guess we'll square root both sides. So if you square root 12.5, it comes out to 3.535 or 536, I guess. And let's see what they asked us around to, or if they did at all. Nope, they did not. So that'll be your side length right there. And then I guess probably good habit to put your units. Um, and cubic inches, so I'm assuming, everything is in inches here, so I'm assuming this side length is going to be inches right here. And that should be it there for you.